Assalamualaikum. In this video presentation, my group and I will be discussing about determining airborne pollutants using Photoacoustic Spectroscopy or PAS. Our group members are Farah Fadila binti Bakri Muhammad Nur and also me, Nur Alia binti Hazrin.
Assalamualaikum warahmatullahi wabarakatuh. My name is Farah Fadila. So now let's dive into photoacoustic spectroscopy, or we call it PAS. It's such a powerful technique used to detect airborne pollutants. PAS also works by detecting the acoustic signal generated when gas molecule absorbs the modulated light, typically from a laser source. This technique has some remarkable advantages over other traditional methods. PAS also has an impressive detection limit, reaching ppb to ppt, which make it highly sensitive for monitoring pollutants in the atmosphere. Other than that, it also will allow for real-time monitoring, providing immediate results, which is critical in environmental health management. This is particularly we use for detecting harmful gases such as like carbon monoxide or sulfur dioxide, also nitrogen dioxide. One of the key highlight PAS is its small size, that's making it more portable and also affordable compared to FTIR and UV-VIS. Alright, so we will look more about PAS in the next slide, and we will compare other methods too, and the potential improvement that can be made to enhance its functionality. Okay, now let's dive into the process of how photoacoustic spectroscopy, or we call it PAS, works in detecting airborne pollutants. So I will walk you through each key step involved in this technique. So the first thing is we start with a modulated light source, which is often a laser. This light is tuned to specific wavelength, okay, that match the absorption characteristic of the target gases. Like, for example, we have carbon monoxide, carbon dioxide, nitrogen dioxide, carbon monoxide. So the laser will emit the light that interacts directly with the gas sample. As the modulated light hits the gas molecule, they will absorb the light. So this is going to be the second one in the selective absorption. Okay, when they absorb the light at the specific wavelength, this will lead to energy transition. Okay, energy transition between the molecule, within the molecule, causing them to vibrate, and also heat up. So different gas will absorb light differently. Okay, which is why PAS is so selective in identifying specific pollutants. Okay, so the next is acoustic wave generation. This stage will absorb energy, causes the gas molecule to expand and also contract as they heat up. Okay, this rapid heating result in the generation of pressure waves, also be known as our acoustic waves. Okay, essentially the light include energy causes the gas to behave like a small engine that will create a sound wave. Okay. Next, these pressure wave are then detected by our very sensitive microphone, okay, they are capable of picking up those tiny fluctuation in pressure. Okay, so they are very sensitive. The microphone is very sensitive. The sensor is designed to detect even the faintest of acoustic signals. Alright, so once the acoustic waves are detected, okay, they are converted into electrical signals. So this is our number 5, electrical signal processing. These signals are then processed by specialized electronics and software, which helps to analyze our desired data. Okay, the last thing is concentration retrieval. So by analyzing these electrical signals, we can determine the concentration of the target gas in the sample. So from what we can see, the more intense the acoustic signal, the higher the concentration of the pollutant in the air.
Other gas detection were considered, but other technologies did not meet the high-level sensitivity, mineralization capabilities, or the real-time ability of photoacoustic spectroscopy or PAS. In comparison to UV-VIS or FTIR, which are usually large in size and can only be used in laboratory, PAS is portable and can be used in the field. Compared to electrochemical sensors, PAS also has a far better sensitivity and significantly lower detection limits, which is down to parts per billion and even parts per trillion. In this article represent the result of finite element method or FEM simulation of the acoustic of a miniaturized H-shaped photoacoustic cell. This technique enabled the researchers to study the behavior of various gases at particular resonance conditions, and they did not feel the need to make the device before proceeding to analyze it. Among the most prominent conclusions, it was established that the maximum acoustic pressure was detected at first natural frequency of the gases. That is noteworthy since it informs us that that to detect the signal optimally, we have to put the pressure sensor at the frequency. The table below gives the summary of the resonant frequencies and the quality factors of carbon dioxide, nitrogen oxide, and sulfur dioxide. The Q value of nitrogen oxide and sulfur dioxide are a little higher than carbon dioxide. This implies that the energy loss of their signals is lesser and therefore they detect with much sensitivity. As shown on the left graph, we can find the sudden peak around 18.101 kHz, indicating the resonance frequency of carbon dioxide. The more acute the peak, the more powerful and concentrated the acoustic signal. The sharpness is what measured by the quality factor, which I explained in the table before. The other thing to note with the system is the temperature stability. The graph on the right indicates that the resonant frequency moves upwards with a rise in temperature, and it is a linear and predictable relationship. This implies that the system could be set up so as to be correct under various environmental conditions. Notably, the cell miniaturization considerably decreased background noise, particularly the one related to window absorption of conventional system. This helps increase signal-noise ratio, enhancing clarity of measurements.
Now, let's take a look at the limitation, advantages, and also possible improvement of PS. So, one limitation about PES is ambient noise. So environmental factors like temperature, humidity, and also pressure can also interfere with the measurement, that making it less accurate in certain conditions. Okay, another issue that we can see from PAS is its limited spectral range. Okay, meaning that PAS may not detect all types of pollutants, especially those that don't absorb well in the mid IR range. Okay, so the next one is we have calibration, which also we can take it as our environmental factor as well. So calibration is important for PAS to work properly. So then it needs regular adjustment to ensure the accuracy and environmental factors like temperature, humidity that also can affect its reading. So let's take a look for the advantages. PAS we can see has many strengths. So firstly, it is highly sensitive, which is it can be able to detect pollutants even in a very small amount. They make it a very great for early detection in areas with low pollution levels. Other than that, it is also non-destructive, meaning that it doesn't change or it doesn't harm the sample that being analyzed. Okay, so another great feature is real-time detection, so which make it helps to make a quick quick decision in monitoring our air quality, for example. Finally, PS is also selective, which it can target specific gases like NO2, SO2, carbon monoxide to give more accurate result for those pollutants. Okay. So last thing we are going to take a look the potential environments and potential improvement that we can see from our PS. So there are some. The first thing is signal processing. So we need to enhance the way the system handles the background noise that can make our PS more accurate. Other than that is spectral range. We can expand its ability to detect more types of pollutants that will make our PS more versatile. Other than that is miniaturization, which is make it smaller, make it portable. Okay, we make our PS device much smaller, more portable, that will allow for easier use in different environments. Okay. Next is auto calibration. So by implementing automatic calibration, we would reduce the need for manual adjustment. Okay, so we can do it manually, making it PS easier to use. Okay. So the last thing is environmental compensation. So from improving our PS ability to adjust for environmental changes like temperature, humidity, I believe that it would help keeps it readings much more accurate. Thank you. Now let's discuss the key aspect of PAS. So the first is accuracy. So basically PAS is very accurate. Even at low concentration of pollutant, it can detect trace amount of gases, making it ideal for monitoring air quality in places where pollution levels are very low. About the precision, PAS show consistent results when measuring the same pollutant multiple times. So which it can make it reliable for continuous monitoring over long periods. The sensitivity, PAS is very and highly sensitive, capable of detecting pollutant at very low levels, down to the parts which is PPT, part per trillion. This allows early detection of pollutant before it becomes very harmful. about the detection limits of PAS is very low, meaning it can find pollutants before they can reach the danger levels. Okay, this is particularly useful for early intervention in areas like factories or cities. Okay, the selectivity of PAS, it can be tuned to detect specific gases like NO2, SO2, CO, and else. It works best with gases that absorb in the mid-IR spectrum, but it might not detect other gases as well. Robustness, so generally it robust, but environmental changes like temperature or humidity can affect its performance. However, with better calibration and adjustment for environmental factors, its reliability can be improved. So, yeah.
In conclusion, the research showed that miniaturized PAS is useful, portable, and cost-effective way of detecting greenhouse gases. PAS has great promise in smart city application due to its high sensitivity, good signal-to-noise ratio, as well as good stability during temperature variance. It is recommended that future efforts be directed into making the physical device and putting the system through tests in realistic scenarios and controlling the interface of humidity and other gases. The list shown is the references that we used to do this video presentation. That is all from us. Thank you.